Welcome to another video. Our previous video introduced some of the limitations or recent criticisms of instrumental variables estimation, and also introduced the notion of partial identification as a potential alternative to instrumental variables if we are not confident that the instrument is valid. And in today's video, we'll formalize this notion of partial identification by thinking about benchmarking the degree to which our treatment effect estimate changes as we add more controls in the model as a way to further benchmark against controls that we don't observe and can never observe. This has some positives and negatives. The big positive is that we can be very transparent and only use the data to come up with plausible bounds. The downside is that we don't have a single number for our treatment effect, we have an interval instead. Let's start by setting up the problem formally and then seeing how the correlation between treatment and other observables in the model can be informative about the causal effect of treatment. We're going to consider a linear model with cross-sectional data, and the key variable on the right-hand side is going to be D, which is our treatment indicator. And then we have other covariates denoted with X, and then unobservables denoted by epsilon. And for now, we're going to assume that the X's are exogenous, but we are also going to assume that the treatment is potentially endogenous, meaning that there's some correlation that's non-zero between D and epsilon. So how can D and epsilon be correlated? You might be thinking, well, I thought that epsilon was independent of all of the X and D. Well, it's helpful to rewrite this equation in a different form. And in this form, we're recognizing that there are other covariates, W, that we can't observe that are embedded in epsilon, so that epsilon is a combination of a pure noise term, which we're denoting by nu here, and an index of unobservable covariates, W times gamma. And for now, we'll assume that X and W are uncorrelated, and we can just assume that nu is exogenous to everything. So the key idea here is that we have these W's that are unobservable to us, or that we chose not to include in the model. And just to introduce some terminology, we call the correlation between D and X beta the selection on observables. We call the correlation between D and epsilon the selection on unobservables. And this selection on unobservables is the main problem with doing OLS in the first place, because we can't adjust for this unobservable selection because we can't see what's unobservable by definition. And we can always measure the correlation between D and X beta, but we can never measure the correlation between D and epsilon. And we need both pieces of information if we're going to pin down what the causal effect of D is on Y. So the question is can we make some assumption about the correlation between D and epsilon based on what we see as the correlation between D and X beta? So if we reproduce that equation at the top of this slide and state it differently, the key question is, can we use information about the correlation between D and X beta to learn about the causal effect of D on Y? And there's a couple of extremes that we can pursue that could be useful in this endeavor. First, we could assume that there's no confounding in our model. This is equivalent to assuming that the correlation between D and epsilon is 0. And then on another extreme, we could assume that there's equal correlation between D and X beta and D and epsilon. So this would arise if, for example, X was a random subset of the union of X and W. This is non-standard notation, but hopefully you get the idea that if I have the whole universe of relevant covariates and I randomly sample from them, then I'm going to have roughly equal correlation between D and X and D and W. So then the intuition is that we take this information about whatever we choose to assume about the correlation between D and epsilon and the correlation between D and X beta, and then we use that to properly shade our estimate of alpha hat. So if alpha hat was positive and there was positive selection into D, then our treatment effect alpha hat would be closer to 0 than our OLS alpha hat. So the steps that we follow to get to this solution are as follows. So first we regress Y on D. Then we regress Y on D and X. And why is this useful? Well, this can tell us about the correlation between D and X beta. If we sort of compare how much did alpha change across steps 1 and 2, and how much did the r² change across steps 1 and 2. So that's step 3, is to make that comparison or make note of what you're seeing in the data. And then we need to make some assumption about the relationship between selection on observables and selection on unobservables. So typically we'll assume some scalar value of lambda, and lambda could be 0, in which case we would be assuming exogeneity, or lambda could be 1, in which case we're assuming equal selection. And typically we would choose some value between 0 and 1. And then finally, we can use all of this information to get a plausible interval in which the true treatment effect alpha hat falls. And we won't get into the specifics of how to do that in this video, but we will in a few videos from now. So that's the basic intuition for what we're going to do when we want to use sensitivity analysis to think about how much our selection on observables estimate of the treatment effect is going to be confounded by additional unobservables that we can't put into our model. Our next video will go through some of the papers that have formalized these approaches and been used by practitioners. And then in a couple of videos, we'll go through an actual coding example with real data to see how these things work in action. So I hope that you've enjoyed this video so far, and that I'll see you in the next one as well.